Example 1 is asking us to consider the following function. It's a nice polynomial here. Where is the function concave up and where is it concave down? So I'm going to be using my second derivative primarily to answer this question. We already know that if the second derivative in an interval is positive, the function is concave up there. And if it's negative, the function is concave down. So let's just go ahead and compute the first derivative and then the second derivative. F prime of x is going to be equal to 3x squared minus 12x plus 9. Then the second derivative is going to be equal to 6x minus 12. Now we're going to go ahead and we're going to set the second derivative equal to 0. And when we do that, we're going to have 6x minus 12 equals to 0. 6x is equal to 12. X is going to be equal to 2. So then this is now telling us that we are pretty much ready to investigate the sign of the second derivative. I will position 2 right here. If you remember, the second derivative is equal to 6x minus 12. In fact, let me rewrite it as 6 times x minus 2. So then I'm going to go right here on top of my number line and I'm going to write the second derivative. I will also put a heavy dot at x equals 2, indicating that the second derivative is equal to 0 there. And then I'm going to start investigating the sign. So if I pick a test point, let me choose something easy. A point, a value that is less than 2, something like 0. If I plug in 0 for x right here, I'm going to get a negative number. So my second derivative here is less than 0. That means that my graph is going to be concave down in that interval. Then I'm going to choose another x value randomly, a value that is bigger than 2. Let's say 3. And if I plug in 3 for x, I'm going to have 3 minus 2, which is positive. Then that means that my graph is concave up in that interval. So I found the intervals of concavity. My conclusion, therefore, f is concave up. I'm going to use the abbreviation CU just to save time for concave up. F is concave up in the interval from 2 to positive infinity, and F is concave down in the interval from negative infinity to 2. This is essentially what you're always going to do when trying to investigate concavity using the second derivative. You're going to find the first derivative, the second derivative. You're going to set it equal to 0 so that you can find out exactly that turning point. When you do that, you're going to go ahead to your number line and you're going to locate those values of x where the second derivative is 0. And then you have to remember that this is the investigation for the second derivative. So this is why I chose to write the second derivative expression right here. And then you're going to look at your intervals and you're going to choose a test point, any test point. Keep it simple, something that allows you to do things mentally, if possible. I chose 0. If I plug in 0 here for x, I get a negative number. So getting a negative number is telling me that in this region right here, the second derivative of x is going to be less than 0. So then my graph is concave down. And then when I choose a test point right here, something like 3, the second derivative is positive. So I know that f double prime of x is going to be bigger than 0, and that really implies that my graph is concave up. So immediately I state the two intervals and I already know the concavity of the graph. In example 2, we're being asked to consider g of x. Now x is between 0 and 2 pi. And they're asking where is the function? Again, is concave up and where is it concave down? So we're going to go ahead and we're going to find the first derivative. The first derivative will be 1 minus 2 times the derivative of cosine, which is negative sine x. That means that we're going to have 1 plus 2 sine x. Then the second derivative. That's going to be equal to 0 plus 2 times cosine of x. Setting the second derivative equal to 0, so set g double prime of x equals 0, means that 2 cosine of x is equal to 0. In other words, cosine x is going to be equal to 0. So now, thinking of cosine, the sinusoid, its graph, for instance, where is cosine of x equals 0? Let me actually quickly draw a sketch of the graph. So we have something like this in the interval from 0 to 2 pi. This is x right here. This is the second derivative. It is equal to 0 precisely here at pi over 2 and right here at 3 pi over 2. So then that means, let me continue here, that means that the cosine of x equals 0 when x is equal to pi over 2 comma 3 pi over 2. And now that I found those turning points, I am ready to do my second derivative analysis. So this is for the second derivative. Actually, we're using g. So g double prime of x. If you remember, this is g double prime. So let me write that down here. 2 cosine of x. Then I'm going to start positioning the 2x values that I got. So here is 0. And 0 is going to be the left endpoint. Then we're going to have the right endpoint right here, 2 pi. I can even put 0 there because you know that we avoid the derivative is never taken into account at the endpoints. We assume that g is not differentiable there. Then we're going to have over here pi over 2. I'm putting a heavy dot indicating that the derivative is equal to 0 there, and the same thing for 3 pi over 2. And now it's time to start investigating the sign of the second derivative. So the sign of 2 cosine of x. But I believe that I can nicely use this graph over here, because if you remember, this was the graph of y equals cosine. Because I have a 2 in front and it's a positive 2, that 2 doesn't affect the sign of the second derivative. So let's see. From 0 to pi over 2, cosine is above the x-axis, so cosine is positive. That means that I'm going to put positive over here. Then we're going to go from pi over 2 to 3 pi over 2. Cosine is below the x-axis, so cosine is negative in this interval right there. Then we're going to go from 3 pi over 2 to 2 pi. Cosine is above the x-axis, so cosine is positive there. So then that means that the second derivative, oops, I keep putting f. Let me go back to g. G double prime of x here is bigger than 0. G double prime of x here is less than 0. And g double prime of x here is bigger than 0. So then that means a positive second derivative, concave up, then concave down, and then concave up. Therefore, we will say that g is concave up in the interval from 0 to pi over 2, and also from 3 pi over 2 to 2 pi. And we will say that g is concave down in the interval from pi over 2 to 3 pi over 2. Example 3 is asking us to consider the same functions of example 1 and 2. I'm doing that so that we don't have to redo pretty much the same work. So I'm using the same functions. Are there inflection points in each of these cases? So if you remember, this was the second derivative analysis for the f of x function, the first one right here, the polynomial. And when we did the second derivative, we did the number line, we found that indeed there is a change in concavity. On the left of 2, the graph is concave down, and on the right, concave up. Just quickly though, you also have to make sure that the function is continuous at 2, the original polynomial, and polynomials are continuous everywhere in their domain. So we will say here, number 1, we will say since f is continuous at x equals 2, and second statement, since concavity changes around x equals 2, then f has a point of inflection. It has a point of inflection at x equals 2. In other words, the point of inflection will be 2 comma f of 2. I am going to skip calculating f of 2, but if you actually need to know the value, then you know that you're going to go back to the original function, plug in 2 everywhere you have an x, do your calculations, and boom, you have the y value. For the other function right here, for g of x, which is this function made up of x and a trigonometric function, we found that this was the second derivative analysis for that function. We found that in this interval, the graph is concave up, then it transitioned to concave down. There is a change of concavity at pi over 2, and there is another change of concavity at 3 pi over 2. And the original function, g of x, is continuous at pi over 2 and 3 pi over 2. So then again, we know that in this case, g is continuous at x equals pi over 2 and 3 pi over 2. Second of all, we know that concavity changes around these values. It does. We can see it above. What is the conclusion? Therefore, indeed, G has points of inflection at x equals pi over 2 and 3 pi over 2. And those points of inflections are going to be pi over 2, comma, g of pi over 2, and then 3 pi over 2, comma, g of 3 pi over 2. And if you had to calculate those values, then it becomes a simple algebraic approach. You're going to go to g of x and plug in pi over 2 for x, pi over 2, take your time, do the calculations, and you're going to have your y value. I also want you to notice that points of inflections in these two functions only happens where their second derivative is equal to 0. These functions are differentiable everywhere. They are twice differentiable. So we are not going to have points of inflection coming out of sharp corners. There aren't any. This is a beautiful polynomial that is differentiable everywhere, even twice differentiable. And the same thing for g of x. Twice differentiable. So the only inflection points are coming out of their second derivative being equal to 0. That's how we found those inflection points. Example 4 is giving us a function, f of x equals x to the 5/3, and is asking us to find inflection points. This is a new function. We haven't worked with it yet, so we're going to go ahead and do the same thing as before. We're going to find the first derivative and the second derivative. f prime of x is going to be equal to 5 over 3 times x to the 2/3. I'm using power rule. Then the second derivative, f double prime, is going to be equal to 5 over 3 times 2/3 times x to the negative 1/3. Simplifying a little bit, we are going to have 10 in the numerator divided by 9x to the 1/3. So this becomes the second derivative. Now, in order to find in order to find possible places where we may have points of inflection, we have to remember that points of inflection may happen where the second derivative is equal to 0 and possibly where the second derivative does not exist. So these are the two cases that I have to consider. Where will the second derivative equal to 0? And also, where will the second derivative of x does not exist? So D and E for does not exist. So if I take the second derivative, for example, if I look at this expression right here, you notice that because the second derivative is a fraction, the only way that it will be equal to 0 is if the numerator is 0. But the numerator is just a numerical coefficient. It's just 10. There's no variable here. Then that means that the second derivative will never be 0. Another way that you can do that, if you want to, is to do it algebraically by taking the second derivative, set it equal to 0, put it over 1, and then try to cross multiply. Pretend that you want to solve for x. And when you do that, notice how the variable expression multiplies with 0, and anything times 0 is 0. So you're going to get the 0 is equal to 10, which is completely false. So then that means over here, no solution. Okay? So no possibility of getting an inflection point from setting the second derivative equal to 0. So now let's go on to the other possibility. What happens? Can the second derivative be undefined? And then, if again we go back over here on the left and we look at that denominator, we actually have a variable there. So if x is equal to 0, the second derivative will be undefined. So the second derivative does not exist exactly when x is equal to 0. But now, before I declare this as a possible place where I may have a point of inflection, I have to make sure that that the function is continuous there. And if I go back to the original function, f of x is beautifully continuous. So we're going to say over here, or we're going to make a note, that f is indeed continuous at x equals 0. So now what I have to do is to check whether concavity changes there. So in order to do that, you're going to draw your number line. This will be for the second derivative. The second derivative is equal to 10 divided by 9, x to the 1/3. You will position 0 right here. I'm going to put an open circle to indicate that the second derivative does not exist there. And then we're going to pick a test point. What happens if I choose -1? If I plug in -1 in place of x here, I am going to get a negative value. That means that my graph is going to be concave down when the second derivative is less than 0. Then if I choose a test point, something like 1, and I plug in 1, I'm going to get positive second derivative. Second derivative is bigger than 0. So my graph is concave up. So then that means that concavity changes. So we will say that since concavity changes at x equals 0, then indeed, then f has a point of inflection. It has a point of inflection at x equals 0. In fact, the point of inflection is going to be 0, comma, f of 0, which is just going to be 0, comma, 0, the origin. Example 5 is asking us to use the same functions of examples 1 and 2 and to use the second derivative test to identify local extreme values. If you remember, the second derivative test is not for concavity or points of inflection. It is for local extrema. So what we need to do there, according to what that test is saying, we're going to find the first derivative so that we can find the critical points. So first derivative, f prime of x, that's going to be equal to 3x squared minus 12x plus 9. Now we're going to go ahead and find the critical points. The critical points are found by taking the first derivative, the quadratic that we just got, and setting it equal to 0. And then trying to solve this quadratic. I'm going to factor a 3 out. That's going to give us x squared minus 4x plus 3 equals 0. And then the quadratic should be factorable. That's going to be x minus 1, x minus 3. So we end up getting that x equals 1 and x equals 3 are the solutions of this equation. Now, for these points to be critical points, we have to quickly check that the function is defined at those points, and the function is perfectly defined. X equals 1 and x equals 3 are in the domain of the function. So, conclusion, the critical points are indeed going to be 1 and 3. So this is where the function may have local maximum, local minimum. Instead of doing the first derivative test, though, I'm going to proceed with the second derivative test. In order to do that, we're going to find the second derivative of the function. That is going to be 6x minus 12. And then we will start evaluating the second derivative at 1. In other words, that's going to be 6 times 1 minus 12. That's going to give me negative 6. And negative 6 is less than 0. What is that telling me? That is telling me that my function f has a local maximum at x equals 1. Now I'm going to go ahead and consider the second derivative at the other critical point, at 3. That's going to be 6 times 3 minus 12. That is going to give me 18 minus 12, so therefore 6. And 6 is bigger than 0. That is telling me that f has a local minimum at x equals 1. Okay. So that's another way. The second derivative test is another way to test critical points for local maximum and local minimum. Now on to the other one, g of x. We're going to do the same thing. We're going to find the first derivative. The first derivative is equal to 1 minus 2 times negative sine x. That is going to be equal to 1 plus 2 sine x. Now we're going to go ahead and find the possible critical points by taking 1 plus 2 sine x, setting that equal to 0. So then that means that the sine of x will be equal to negative 1/2. Negative 1/2. So where is sine negative? Just quickly over here. Sine is negative whenever y is negative. So then that means in the fourth quadrant and in the third quadrant. And just by quickly solving this equation here, we're going to get that sine is equal to negative a half precisely when x is equal to 7 pi over 6, because this reference angle right here happens to be equal to pi divided by 6. So then the angle in the third quadrant will be pi plus pi over 6, and this is exactly how I get 7 pi over 6. Now on to the other one. Again, this angle right here, as a reference angle, will be equal to pi over 6. So when I look for the angle in the fourth quadrant in standard position, one way to find that angle is to say 2 pi minus pi over 6. That will be 11 pi divided by 6. So then the other one will be when x equals to 11 pi divided by 6. Now I have to quickly go back and refer to the original function. Is my function defined at these values? Are these values in the domain? And the answer to that is clearly yes. So then these are valid critical points. These are the critical points. So now that I found those critical points, I'm going to go and continue with the second derivative. The second derivative of the function will just be 2 times the cosine of x. And then I will take the second derivative at each of the critical points. 7 pi over 6, that is going to be 2 times the cosine of 7 pi divided by 6, which is going to be equal to 2 times negative square root of 3 over 2. That's going to be negative square root of 3. And this is less than 0. So what is my conclusion here? That G has a local maximum at x equals 7 pi over 6. Now I continue with the second derivative at 11 pi over 6. Same idea. 2 times the cosine of 11 pi over 6. That is going to be equal to 2 times the square root of 3 divided by 2. That is going to be equal to the square root of 3. And this is now a number that is bigger than 0. So the conclusion here is that G has a local minimum at x equals 11 pi over 6.